Welcome to my class 12 physics, chapter that is alternating current, and today we will discuss about AC voltage applied to an inductor, or that is also known as AC circuit containing inductor only. Inductor means here this one is the inductor that looks like a coil, clear? And here we will discuss about first draw the circuit diagram. Next we will calculate the instantaneous value of the current. Next, that is the phase difference. Between alternating EMF and alternating current. E for alternating EMF, I for that is the alternating current. Next one, we will draw the phasor diagram. Next we draw the graph between E and I versus omega t. Omega t is the phase. Omega t is the phase of the alternating EMF or phase of the current. Next, we will calculate the instantaneous value of a power supplied and then average power supplied. And the last point, that is inductive reactance. Inductive reactance, or for inductive reactance here we write the symbol that is XL, clear? And the first one is the circuit diagram. We draw the circuit diagram here. These are the external wires. This is also the external wire, and here a inductor is connected. This is the inductor that looks like a simply coil. These are the external wires, and here we connected SC. This one is the SC. This is the symbol of SC, that is the symbol of alternating voltage or alternating current. If this one is the alternating voltage or alternating EMF, we write that is E. E is equal to E0 sin omega t. This is the applied EMF. This is the applied EMF. Clear? Here E is the instantaneous value of the applied EMF. E0, you know, that is the peak value. Here omega t, that is the phase. Clear? And you close the circuit. These are the external wires. These are the external wires. Now the circuit is closed. And here for inductor we write that is L. L for self inductance. L for coefficient of self induction, or that is also known as self inductance. Clear? And this one is the circuit diagram. This one is the circuit diagram. Here alternating EMF is applied and a single inductor is there, so that this is known as AC circuit containing inductor only. Clear? Suppose resistance of this circuit or resistance of inductor, that is very negligible. We write, suppose let resistance of inductor is very small. Very small means R is tends to 0. If resistance of a inductor circuit is tends to 0 or negligible, then this type of circuit is known as purely inductive AC circuit. Purely inductive AC circuit means its resistance is very small. Resistance is negligible. Clear? Then we will calculate instantaneous current. That is instantaneous alternating current. And before that, you know the Faraday's laws of electromagnetic induction and Lenz's law. In the chapter electromagnetic induction, Faraday's laws of electromagnetic induction. What is that? Suppose we take a magnet, bar magnet. This one is the bar magnet. This is the one pole of the bar magnet. We write suppose that is north pole. This is another pole of the bar magnet. We write suppose that is the south pole. And you know, in air or in vacuum, lines of force or magnetic lines of force always starts from the north pole and ends at south pole. And these are the magnetic lines of force. These are the magnetic lines of force. And near the magnet, magnetic lines of force are closely packed, or distance between two magnetic lines of force is very small as compared to this one. So that near the magnet, magnetic field is maximum. And if distance is gradually increased, magnetic field is gradually decreased. Clear? Suppose here we take a coil. This one is the coil. Suppose coil is situated at point A. Then what happens? Now at point A, if we placed a coil, your total number of lines of force passing through this coil is only one. This one. Only one lines of force is passing through the coil, and that is known as the flux. So that we write flux phi 1 is equal to 1. This is the flux. Flux means number of lines of force crossing through a area is known as flux, and your total number of lines of force crossing through this coil is only 1. So that we write flux is 1. That is at point A. Clear? And initially both are at rest. Both coil and magnet both are at rest, so that magnetic flux is always fixed. Always fixed means that is constant. That means always 1. If we move the coil towards the magnet, then this is the new position of the magnet. We write suppose that is B point, and at point B what happened? Now the coil is very close to the magnet, so that the number of lines of force passing through this coil is 1, 2, 3. So that we write in this case flux, that is phi 2 is equal to 3. That means magnetic flux is not constant. If we move the coil towards the magnet, magnetic flux is not constant. Magnetic flux change with respect to time. If magnetic flux change with respect to time, we write that is change in magnetic flux with respect to time, that is d phi by dt. Then what happens? If magnetic flux is changed, then a induced EMF is produced. A induced EMF is produced through this coil. That means a induced current, alternating current, or a induced EMF is produced through this coil. And that induced EMF, we write that is E is equal to d phi by dt. and you put a negative sign from Lentz's law, and you know also the Lentz's law. Lentz's law gives the direction. Lentz's law gives the direction of the induced EMF, and for negative means that is in the opposite direction, or that oppose which produced it. So that here you put a negative sign we get from the Lentz's law. That is the induced EMF produced, that is E is equal to minus d phi by dt. That is the Faraday's second law of electromagnetic induction. You know that. Clear? Suppose, look at the circuit diagram. Here magnitude of the current is not constant. Initially that is increased. This is the maximum value, again decreased, because that is alternating current. If magnitude is not constant, current flowing through this circuit is also not constant. If current is not constant, then what happens? If current flowing through a coil, then you know magnetic field is produced. If current is not constant, magnetic field produced inside the inductor is also not constant. That means magnetic field is changed. If magnetic field change, magnetic flux also change. That means for alternating current, if current is changed continuously with respect to time, magnetic field is changed and magnetic flux is changed. That means magnetic flux, that is phi depend upon current. If you increase the current, field is increased, flux is increased. Clear? Just like this. Here magnitude of the magnetic field is maximum, so that flux is maximum. Here magnitude of the field is minimum, so that flux is minimum as compared to point B. That means phi is directly proportional to I. You know this formula in the chapter electromagnetic induction. That implies we write phi is equal to, here you put a constant, L multiplied by I, and this L is known as the coefficient of self-induction, or you also write that is self-inductance. That is also known as self-inductance, or simply we write that is a constant. We write suppose d phi by dt, this is equal to L is a constant, we write L multiplied by di by dt. What is d phi by dt? You know d phi by dt, in place of d phi by dt we write that is minus E. So that in place of d phi by dt we write minus E, or we write E is equal to minus L into di by dt. This is the induced EMF. Clear? That means finally we get, if we applied a alternating EMF to a inductor circuit, then another induced EMF is produced. That is E induced is equal to minus L into di divided by dt, this one. That means two EMF is there. One is applied EMF and this one is induced EMF. Here a negative sign is there. That means the direction of this induced EMF is just opposite to the applied EMF. We get this from the Lentz's law. And you know in the chapter electromagnetic induction, this one. Clear? Now we derive the equation for instantaneous current. Here we applied the Kirchhoff's loop law. Kirchhoff's loop law. What is Kirchhoff's loop law? That is also known as Kirchhoff's voltage law. And you know this law in the chapter current electricity. What is that? In a closed circuit, sum of total EMF is equal to sum of product between current and resistance. This is the Kirchhoff's loop law. Clear? And here, that is a purely inductive circuit. In case of a purely inductive circuit, you know, resistance is very negligible. That means resistance is 0. So that you write sum of all EMF. Sum of all EMF means your two EMF are there. One is applied EMF another is induced EMF. That means this EMF, applied EMF plus induced EMF. We write for applied EMF, we write E. For induced EMF, we write minus L di divided by dt is equal to, in place of R, we put 0. This is the equation. And from this equation, we will calculate the value of current, instantaneous current. That implies we write L di by dt is equal to E. That implies di is equal to, we take L and dt to the right hand side, so that this is E by L multiplied by dt. That implies you write di is equal to, what is E? This is the applied EMF, this is the applied alternating EMF, and you know the equation for applied alternating EMF. In place of E, we write E0 sin omega t divided by L multiplied by dt. That implies we write di is equal to E0 by L multiplied by sin omega t dt. What is the total current? Total current is equal to sum of all the small current. So that from this expression we write, that implies total current is I is equal to integration of di. This is equal to integration of E0 by L multiplied by sin omega t dt, and E0 by L, this is a constant, we take out of the integration, so that the remaining is, we write instantaneous current I is equal to E0 by L integration of sin omega t dt. And you know the formula of integration, this one, integration of sin theta d theta is equal to minus cos theta, you know this equation. That means we write simply, that implies I is equal to, that is minus, so that you put a negative sign, E0 by L and integration of sin omega t, that is here theta is there, here omega t is there, that means in place of theta we write that is omega t, so that this is cos omega t, and here the extra term is there, that is omega, so that we divided by omega. This is the integration. That implies we write instantaneous current I is equal to minus E0 divided by omega L into cos omega t. And you put the trigonometric formula, you know the formula, this one, you know this formula, cos theta is equal to sin 90 degree minus theta, you know this formula. That implies cos, in place of theta, here omega t is there, so that in place of theta we write omega t is equal to sin, in place of 90 degree we write pi by 2, in place of theta we write omega t, so that in place of cos omega t we put this one. That implies we write I is equal to minus E0 divided by omega L, in place of cos omega t we put sin pi by 2 minus omega t. Clear? Here again we put another trigonometric equation, that is, you know, sin of minus theta is equal to minus sin theta, or we write sin of minus, in place of theta we write suppose omega t is equal to minus of sin omega t. We put this equation here, so that we write, that implies instantaneous current I is equal to, in place of minus sin theta we write, in place of minus sin theta we write sin of minus theta, so that sin of minus theta, sin of minus theta means we write that is E0 by omega L into sin minus pi by 2 minus of minus omega t, this is omega t minus pi by 2. This is the final expression of instantaneous current. Clear? And your omega L is there. In place of omega L, we write simply that is XL. That implies we write finally I is equal to E0 divided by, in place of omega L, we write XL into sine omega t minus pi by 2. Here we write in place of omega L, that is XL. What is XL? In this case, XL is known as inductive reactance. And we will discuss about inductive reactance. Clear? Then we write that implies I is equal to, here we put the Ohm's law. You know the Ohm's law. Ohm's law is equal to V is equal to IR. You know this law. That implies I is equal to V divided by R. Clear? That implies here in place of V, here E0 is there. So that we write E0. In place of R, here XL is there. We write XL. So that in place of I, we write that is I0. That is the peak value. That is the peak value of the alternating current. So that in place of E0 divided by XL, we write the peak value. Peak value is I0. That means the expression becomes I is equal to I0 into sine omega t minus pi by 2. And this is the instantaneous current. This is the instantaneous current. Clear? And alternating EMF, applied EMF is given. You know the equation of the applied EMF, that is E is equal to E0 sine omega t. This is the equation for applied EMF. You know this equation. This is the applied alternating EMF. Suppose this is equation number 2. This is equation number 1. If we compare equation 1 and 2, what happens? In case of applied EMF, this is the phase. Phase is omega t. But in case of instantaneous current, this is the phase. Phase is omega t minus pi by 2. That means a difference of phase is there. And difference of phase, that is pi by 2. And here minus pi by 2, not plus pi by 2. And you know minus pi by 2 means that is lags behind, not leads. Leads means plus pi by 2 or ahead. Ahead or leads means plus. Minus means that is lags behind. That means from these two equations, we write current lags behind an angle pi by 2 radian as compared to EMF. Clear? And this pi by 2 radian, that is known as the phase difference. That means in case of a AC circuit containing inductor only, phase difference between current and EMF, that is pi by 2. Clear? Now you draw the phasor diagram. That is the next point. Simply you draw the phasor diagram. And there are two phasors are there. One phasor, that is the EMF, E is equal to E0 sin omega t. Another phasor is there, that is current phasor, that is I0 into sin omega t minus pi by 2. Now I take two axes. This one is your x-axis, sorry, this one is your y-axis and this one is x-axis. This one is y-axis, this one is x-axis. First we draw the EMF phasor. Suppose this one is the EMF phasor. And maximum value, this is the maximum value. For maximum value, we write E is 0 because this is the peak value. This point is the starting point or origin. Here this is the phase of the EMF. Phase of the EMF is omega t, this one. Phase of the EMF and this angle, we write omega t. Clear? And another phasor is there, second phasor. Second phasor, you know, that is the current phasor, this one. And in case of current phasor, current lags behind. Current here current lags behind an angle of pi by 2. Lags behind means in clockwise direction because this one is the phasor and their phasor is rotated in anti-clockwise direction with angular speed omega, that is known as phasor. Phasor means that is a rotating vector, and in this case this one is the rotating vector. If the rotating vector rotating in anti-clockwise direction with angular speed omega, that is known as phasor. So that this is the forward direction. This anti-clockwise direction is known as the forward direction. If we write plus pi by 2 in this side, we write minus pi by 2, means that is lags behind. Lags behind means in this side. Clear? In this side means clockwise direction. So that we draw the current phasor. Current phasor lags behind pi by 2 angle. Pi by 2 angle. We draw the current phasor. This one is the current phasor. And this is the maximum value of current. For maximum value of current, we write I0. This angle is pi by 2. This one is the phasor diagram because the two phasors are there. One is your EMF phasor, another is your current phasor. Clear? Then we draw the graph between EI versus omega t. Same thing, we take two axes. This one is the y-axis, and in y-axis we take EMF or current. And another axis, second axis, suppose this one is your x-axis. And in x-axis we take omega t, that is the phase. And this point is the starting point, origin, we write O. Up to this, suppose this is half cycle means we write pi. So that this point is the half of the half cycle, we write pi by 2. Up to this is the full cycle means we write 2 pi. And this point is in between pi and 2 pi, that is 3 pi by 2. Clear? And first we draw the graph for alternating EMF. Suppose this is the maximum value of the EMF or peak value. In the negative side, this is also the maximum value of EMF. Then this is the peak value of EMF. This is the peak value of the EMF in the negative side. And you know the equation. Equation is equal to this one. You know this equation. Equation for EMF is equal to E0 into sin omega t. You know another equation for current. I is equal to I0 into sin omega t minus pi by 2. Here omega t means that is omega t plus 0. Omega t plus 0 means initial phase is 0. Initial phase is 0 means the EMF starting from point 0. So that we draw the graph for EMF starting from point 0. This is the maximum value, again decreased, and this is the 0. Again increase in the negative side and reached maximum value, again decreased, and this is 0. This is the graph in between EMF and phase. Phase is omega t. Next we draw the graph for current. Here current lags behind pi by 2 angle. Lags behind pi by 2 angle means in this side. That means current starting from pi by 2. Current starting from pi by 2. Suppose this is the maximum value of the current. Suppose this is the maximum value of the current in the positive side, and this is the maximum value of the current in the negative side. Now draw the graph. We draw the graph. Current starting from this point, and current is maximum at this point. Here also current is 0 and current is maximum at this point. Now draw the graph for current. Maximum value, again 0, again maximum value, again 0. Clear? This is the maximum value in the negative side. And this is the graph for EMF, and this one is the graph for current, because your difference between phase difference between EMF and current is this one, that is pi by 2, and we also get from this equation. And this is all about your phasor diagram and a graph between E and I versus omega t. Next, we will calculate the instantaneous power supplied to a inductor and average power supplied. And what is the instantaneous power supplied? You know the formula for power supplied. Instantaneous power supplied to inductor we write formula is equal to P. You know the formula. P is equal to E multiplied by I. You know this formula from the Joule's law of heating. From the Joule's law of heating effect chapter, that is current electricity, you know this formula. Power is equal to multiplication of voltage or potential difference into current. You know this formula. That implies you write P is equal to, you know E is equal to E0 sin omega t multiplied by, you know the equation for current, that is I is equal to I0 sin omega t minus pi by 2, you know this equation. That implies you write P is equal to, that is E0 I0 multiplied by sin omega t into sin of omega t minus pi by 2. That implies P is equal to, here we divided by 2 and multiplied by 2 into sin omega t multiplied by sin omega t minus pi by 2, and here we put the trigonometric equation. You know the equation, that is sin of minus theta is equal to minus of sin theta. Here we put this equation, so that in place of this we write, that implies P is equal to minus of E0 I0 divided by 2 into twice of sin omega t into, in place of this we write, that is sin pi by 2 minus omega t. Clear? And you also know this equation, that is sin pi by 2 minus theta is equal to cos theta. You also know this equation. That implies we write P is equal to minus E0, we write here, that implies P is equal to minus E0 I0 divided by 2 into twice of sin omega t multiplied by, in place of this one we put this equation, that is the cos theta, so that we write, that is multiplied by cos, in place of theta we write omega t. That implies finally we get the instantaneous power, that is minus of E0 I0 divided by 2 multiplied by, here we put another trigonometric equation, you know, that is twice of sin theta into cos theta, that is sin 2 theta. So that in place of this we put sin 2 theta, we put sin 2 in place of theta, omega t is there. And this is the final expression of instantaneous power supplied. This is the final expression of instantaneous power supplied to an AC circuit containing inductor only. Clear? Then you calculate the average power. Why? Because from the graph, this one is the graph. Here magnitude of the current is not constant always. Magnitude of current is not constant. Magnitude of EMF is also not constant. That means power is not constant. Magnitude of power is also vary with respect to time. So that power is variable, and in case of variable, for total power, we add all the small power divided by from 0 to 2 pi. 2 pi means this is the full cycle. For full cycle we write the time period. Time period is T. That means from 0 to T we calculate the average power. How we will calculate the average power? We calculate the average power just like this. This is the instantaneous power. Next we write its average power. As power is not constant, only for this reason we calculate the average power. That means for average power we write P bar. P bar means this is the average power is equal to average of this one. We write average of minus E0 I0 divided by 2 into sine twice omega t. And in this equation, minus E0 I0 by 2, this is constant. So that we cannot calculate average of this one. Only we calculate the average of sine 2 omega t, because this is not constant. This is variable because this is depend upon the time. So that only we calculate average of sine twice omega t. So that this equation we write that is P bar is equal to minus E0 I0 divided by 2. Average of sine 2 omega t means we write average of sine twice omega t. This is the symbol of average. That implies we write average power supplied is equal to minus of E0 I0 divided by 2 average value. Average value means sum of from time 0 to t all the sine 2 omega t. Sum means that is the integration divided by. For full cycle we write the time period is equal to t. This is the average value. Clear? That implies we write average power P bar is equal to minus E0 I0 divided by twice t into integration of this one. And you know the formula for integration, that is integration of sine theta d theta is equal to minus of cos theta. You know this formula, and we put this formula here. That means we write in place of integration of sine 2 omega t, we write that is minus of cos. Here theta is there. Here in place of theta that is twice omega t divided by, in this equation 2 omega, that is the extra term, so that we divided by 2 omega, and this is vary from 0 to t. Clear? And we take 2 omega out of the integration, so that final value of average power is equal to, we take minus also out of this, minus plus, that is E0 I0 divided by twice t multiplied by again twice omega. This is cos 2 omega t, cos twice omega t, vary from 0 to t. And here omega is the angular velocity. And what is omega? Formula for omega, you know. Omega is equal to angular displacement by time. And for one complete rotation, angular displacement, that is 2 pi. So that in place of theta, we write 2 pi divided by, in place of t, we write capital T, and we also write 2 pi divided by t, that is also 2 pi multiplied by frequency 2 pi f, and in place of omega we put 2 pi by t. That implies average power supplied is equal to E0 I0 divided by 2 into 4 t omega multiplied by cos 2, in place of omega we write that is twice pi divided by t, in place of small t first we put the upper limit, that is capital T, then minus sign, next that is cos 2, in place of omega we write that is 2 pi by t multiplied by, in place of t we put the lower limit is 0, clear. And here t cancel, that is cos 4 pi, and you know the value of cos 4 pi. Cos 4 pi is the same as cos 2 pi, that is also same as cos 0, and cos 0 means that is 1 minus, this is also cos 0 means that is also 1, and 1 minus 1 that is 0, that means this total term is 0, 0 multiplied by something is 0, so that finally we get average power supplied is 0. This is the expression of average power supplied. Instantaneous power is there, but net average power is 0, clear. And the last point, that is the inductive reactance. Last point, that is the inductive reactance. And you know the symbol for inductive reactance. For inductive reactance we write that is XL. XL is equal to omega into L. In place of omega we write that is twice pi F multiplied by L. That implies inductive reactance XL is equal to twice pi F multiplied by L. This is the mathematical expression. This is the mathematical expression of inductive reactance. But what is the meaning of inductive reactance? Suppose a coil is there. This one is the coil, or this one is also known as the inductor. And if a current flowing through this inductor, what happens? If current flowing through the inductor, this inductor opposes the flow of electric current, that means total opposition upward. We also write here that is the total opposition upward to the flow of current, that may be direct current, may be alternating current, but current. That means the total opposition upward to the flow of current by an inductor is called, that is inductive reactance. That means in case of inductor, opposition upward is known as inductive reactance, but in case of resistor, this one is the resistor, in case of resistor, opposition upward to the flow of current, you know that is resistance. That means resistance in case of resistor is the same as inductive reactance in case of inductor, both are same. And you know the unit of resistance that is ohm, so that unit of XL, that is also ohm, and its dimension is the same as the dimension of resistance, clear. And from this equation we write, equation is XL is equal to twice pi F multiplied by L, so that XL is directly proportional to F. XL is directly proportional to F. F is the frequency. First, for alternating current. For alternating current, frequency is that. For alternating current, frequency is that. We draw two graphs, suppose. This is the first graph. And this is the alternating current. We draw another graph for the alternating current. Both are different. In this case, frequency is small. In this case, frequency is greater. Clear? This type of alternating current, frequency is high. This type of alternating current, frequency is low. That means frequency of alternating current is not fixed. Frequency of alternating current may be variable. If we change the frequency, or if we increase the frequency, inductive reactance is also gradually increased. That means for alternating current, inductive reactance is depend upon the frequency. If frequency is small, we write if f is small, then XL is also small. If frequency is high, then opposition effort to the alternating current, that is also high. That means if we take a inductor, an alternating current flowing through the inductor, then the inductor opposes the alternating current. That means simply we write finally we write inductor oppose alternating current, and that depend on frequency. That depend upon frequency. If frequency is low, opposition effort is also low. That means alternating current easily pass through an inductor. Clear? If frequency is high, then inductive reactance, that is XL is also high. That means opposition effort is high. That means current, alternating current passing through the inductor is also very small. Clear? Then for DC, we write for direct current, and this one is the graph of the direct current. This one is the graph of direct current. That means its direction is not changed. Direction is not changed because direct current means its direction always remain constant. Here current is situated in the positive side, so that in this case frequency F is equal to 0 in case of direct current, and we get a direct current from your battery, from your mobile battery, laptop battery, solar cell, we get the direct current. And in this case frequency of direct current is 0. If frequency of direct current is 0, what is the inductive reactance? XL is equal to twice pi F multiplied by L. In place of F we put 0, so that finally we write inductive reactance, that is 0. Inductive reactance is 0 means opposition effort to the flow of direct current is 0. That means direct current easily pass, or we write simply direct current, this direct current easily pass through the inductor. Clear? Direct current easily pass through the inductor because F is 0, so that opposition effort or inductive reactance is 0. That means if we take an inductor, this one is the inductor. If we take an inductor, direct current easily pass through the inductor, but alternating current passing through the inductor, but that is depend upon the frequency. And if here you draw a graph, in case of alternating current, this is the equation. That means inductive reactance is depend upon the frequency. If we increase the frequency, inductive reactance is increased. If we decrease the frequency, inductive reactance is decreased. So that if we draw a graph between frequency and inductive reactance, then we get, if we increase the frequency, inductive reactance is increased. The graph is just like this. Clear? And this is all about your AC circuit containing inductor only, and in the next class we will discuss about third circuit, that is the AC circuit containing capacitor only. And thank you.